So I would like to begin the afternoon session. And the first talk will be by Professor Omer Yehezkeli. Omer is the head of the nanobio interfaces laboratory at Technion. He joined Technion to the faculty of biotechnology 4 years ago, and look forward to hear talk.
Better now. So the work that we are doing in my group is focused on the interface between materials, usually nanomaterials, and biological entities. Part of it is related to enzyme and nanoparticles. We're trying to understand better how can we interface the photoinduced reaction of the unique enzyme nitrogenase, the only enzyme that can reduce nitrogen into ammonia. Another part of this work is the utilization of enzymes to electrodes, and this is for biosensing and biofuel cell device, and I will talk about that today. Other part is related to photo or biotic-abiotic elements or photobioelectrochemical cells, and I will show some examples of how we can use the properties of each or the advantages of each to improve the abilities that we have today. Other part that I will not talk today about is the cyborg organism. Part of our work is actually to create a new bacteria. We are trying to have another organelle inside a bacteria with some nanoelements with new properties, and to use that for catalysis. There is one poster upstairs that you can see some of the data that we have. Okay, so I will start with a disease that unfortunately most of us will know during our life. Something like 10% of the population around the world. Somehow in the Middle East it's even more terrible, the problem. And it's actually a lot of different diseases. And one part of it is, or one important part of treatment is to control glucose concentration in the body. And for that, we need to construct or to have biosensors that can do that. And until now, the only reliable sensors that commercially available are related to enzyme. You need to use enzyme. If you just try to oxidize it by other materials, you have unspecific reactions. And there is several, actually, people talked about it in the morning, Itamar. You can have a mediated electron transfer and direct electron transfer. I will skip that. And the idea is to actually put it inside or underneath the skin in the interstitial fluids. And when you measure it there, you can monitor the glucose continuously. And this is what we are trying to do. And funny fact is that the technology that has been developed in the 60s is still the major technology that people use today. 75% of the devices used today is a technology from the 60s. There is a Professor Adam Eller that used the Abbott. He started the company that lately became part of Abbott. And they measure immediate electron transfer and more sophisticated technology. So all the systems that Itamar presented in the morning and I showed before use glucose oxidase as the catalyst. The problem is that you produce hydrogen peroxide with that, and you actually depend on oxygen. Oxygen level can influence your sensor. A way to skip that is to use glucose dehydrogenase. You can use NAD-dependent glucose dehydrogenase, but then you have a cofactor that is diffusional, and this limits any real applicative methodology, especially inside our body. And recently, the last 10 years, it's become more popular to use FAD-dependent glucose dehydrogenase. The good thing about this enzyme is, first of all, that it is oxygen independent, and this is really important for sensing, and also it's still more stable and have more advantages, and I will show it in a second. So to get to real application and not just to make another system, you need something simple. You need something that you can deposit on any surface. and you need a very good noise, signal-to-noise abilities, and this is what we try to do here. So we use polydopamine that you can easily polymerize by changing the pH. We're using the catalyst that I told you before, the glucose dehydrogenase. This is the alpha subunit of the enzyme, and a redox mediator. So it's a very modular system. We just take the solution that we mix, deposit it on any surface, and we have our sensor. And the nice thing about modular system is the fact that we can change it easily. So at the beginning, we work with DCPAP. It's a good redox mediator that enables us to activate and gain really high bioelectrocatalytic currents. But the problem is that at a potential above 0, you can also oxidize ascorbic acid and uric acid and other interference molecules. So by changing the redox mediator to a lower potential one, we can actually get the same activity, and now all the interference cannot interrupt. And by examining that, we actually confirm that this is not a problem in our sensor. And hopefully we will manage to take it forward, and we already have some very nice results about stability. This is something that if you look in the literature, there is 1,000, maybe more papers about biosensor or biosensing device for glucose. But if you look for stability for more than, I don't know, 5 minutes, you will not find it. Maybe 1 or 2 papers. Our sensor is stable for 3 days, and this is a good beginning without any further coating. And as I mentioned, we can use it on any surface. So we try it on gold, glassy carbon electrode, of course, and also carbon paper, toroid paper, and in all of them we can get a good signal. So it will be easy to scale it up, hopefully, in future devices that we would like to develop. So we have a bioanode and a very efficient one, and we decided to construct a biofuel cell using exactly the same technique. So it's a modular system, as I said, so we can also change the catalyst, the biocatalyst, and the cathode, not just the anode, as I showed before. And we use the bilirubin oxidase. It's an enzyme that enables the reduction of oxygen into water, and by adding to the polydopamine ABTS, a proper redox mediator, now we can gain high bioelectrocatalytic currents, and we can construct a biofuel cell, and this is really nice. In this case, we actually developed or cloned a new enzyme, a thermophilic one. We hope that it will gain us better properties. Actually, it didn't, but this was part of the development. Still, the commercial one is slightly better than the one that we developed. So I talked about sweet sensor, and now we will go to sweat sensor. So another part in biomarker that is really important is lactate. It's a marker for all kinds of diseases. In sport medicine, it's really important. And at this direction, we didn't have any change. Usually people use lactate oxidase, similar to GOX, glucose oxidase before, or NAD dependent. So we found out that we can clone and overexpress in our lab the FMN lactate dehydrogenase, and just recently we got really nice results with the lactate sensor, similar methodology, and we can detect between 0 to 8 millimolar. This is kind of the range that we have on the skin, so it's kind of a stem that we will have on the skin. We can use it for biofuel cell to generate from our sweat energy, or to detect the amount. It's really nice. Interestingly, we can actually have also direct electron transfer with this enzyme. We have a HEM molecule inside of it. So we had our biosensor and biofuel cell, and we thought, how can we utilize it in a different direction? And one of the interesting things, in our world is how to make the world more sustainable. And And if we are taking wood, for example, or biomass, we know that it contains cellulose that is not being utilized for energy. We can burn it, but then we cause to pollution. A nice trick that we did was to combine cellulose complex. It's 3 enzymes that actually enable the breakdown of cellulose into glucose, and then we can just integrate it to the biofuel cell that we constructed before, and with that we could gain energy in a biofuel cell device of 0.6 milliwatt per centimeter square, a really nice advance. We are a little bit stuck. Those cells are good for 32 hours at this point. We're trying to improve it today and in the future. So I will skip to a slightly different direction, mimicking the photosynthesis process. So as we know, we have 2 central proteins, the important one, the photoactive one, the photosystem 2 and photosystem 1. Well, photosystem 2 is actually the engine of everything. It oxidizes water and enables the electron transfer further into, in the end, to the Calvin cycle. But the problem with photosystem 2 is the fact that it breaks down. If you irradiate it, whatever you will do, after some time it will break down, the T1 subunit will fall, and nature just replaces it. We cannot do it in artificial systems, but we know from other fields, from inorganic chemistry, that we can use semiconductors to do the job, and bismuth vanillate is actually an amazing material. It's not cause any pollution, it's quite environmental friendly, and it can oxidize water in the right condition. You can reach 60% Faraday efficiency. And we decided to use bismuth vanillate to replace the PS2 to oxidize water. This is also a work that many other groups did around the world, but we decided to use it in combination with bilirubin oxide, the cathode, the biological cathode that I presented before. And now you should ask why. There is a platinum can reduce oxygen, why not just to stick with material? And to convince you that maybe we should look for something else like the enzyme, you can look on this slide. So the nice thing about the bilirubin oxide is the fact that you have a lower onset potential as compared to platinum at neutral pH. So it's actually more efficient, not current-wise, but potential-wise. So for cell, if we will stabilize it enough, it's worth the effort. And the bilirubin oxide holds inside 4 copper ions. This is 3 copper ions in the catalytic site, and another, the T1 site, is actually an internal redox mediator that enables the activation. And we decided to examine 2 variants, one that we overexpress in our lab, a unique bacterial version of it. Most of it comes from fungi. And we compare between them the thermophilic one that we hope that will give us good or high current, gave us some high current, but also high over potential that we did not expect. The nice thing about this enzyme is the fact that no one ever looked at it or got any crystallographic structure of it, and recently we collaborate and we now have the structure, and it helps us, I will not talk about it today. We also characterize the temperature, and we can work under 50 Celsius. This is important for us for any future application. Use the same trick with the polydopamine to entrap the bilirubin oxidase in ABTS redox molecule, and now we can gain much higher bioelectrocatalytic current as compared to just deposition of the enzyme randomly on the surface of the electrode, and this is nice. We tried it then with our new enzyme and actually got really poor results. As you can see, much lower bioelectrocatalytic currents, and we were puzzled how we can solve it. And then we found a few papers, and they use aromatic molecule to orient the bilirubin oxide, the T1 site. and we play a little bit with software and try to kind of rational design a molecule that will fit our active sites. So we use pyrene moieties for that. And with that, we could improve quite nicely the bioelectrocatalytic current than what we got before. This is nice. Again, you cannot win it all. The stability of those big bilirubin oxidized were poor. As you can see, after a couple of hours, we lose the activity, while the MV BOD maintain activity even through 22 hours on the air or anti-oxygen. We check them both. We also check the power output, and with the bismuth vanillate and the BOD, we can gain almost 1 volt. And with high current, it actually come out with 0.85 milliwatts per centimeter squared. It's quite a nice amount. So maybe just in a few minutes that I have, I will talk about, so we have the bismuth vanillate. This can mimic the PS2. And we thought about a method to have the full Z-scheme configuration. To do the full Z-scheme configuration, we need some mediator between the PS1 and the PS2 to gain higher potential at the PS1, and actually to drive the reaction water oxidation and back. The problem in those systems, in other articles that people recently published, is the fact that you generate hydrogen peroxide. The hydrogen peroxide, in the end, eats the protein or eliminate its activity, and you need somehow to correct that, and people use all kinds of chemicals to react with the hydrogen peroxide. So we thought about the bismuth vanillate. We knew that we can use it as an electron donor to break it down on the surface of our semiconductor. So by taking those anode and cathode close together, we can actually lower the amount of hydrogen peroxide in our system and extend the life of our protein, and this is what we did. We use electropolymerization of methylene blue as the electron donor. We actually were surprised to see that we get some photocurrent out of this layer too. You can read it more in the paper. And we use a polyviologen molecule as the acceptor, and with that we could increase the generated photocurrent. We posted them together. We then moved and used a toroid paper. It's actually carbon paper, as you can see here. And we could see that the protein and the polymer are deposited on the surface. And maybe the most interesting part for me in this work was the fact that we can oxidize the hydrogen peroxide and lower the amount in the solution and extend the life of this cell. And also the polymethylene blue can react with the hydrogen peroxide and also eliminate the destructive effect of this material on the electrode. It's lower our efficiency, but it's helped us to maintain it alive. With that, I would like to thank you all, my great student and group and the funding. Thank you very much.